Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research efforts to develop modeling and monitoring tools for evaluating passive and active remedial approaches for sites impacted by NAPL. First, Dr. Bo Stewart, Dr. Mike Cavanaugh, and Dr. Mark Woodison will present an alternative approach for predicting DNAPL remediation outcomes using a volume average model that is faster and less costly than complex numerical models and also more accurate than simple screening models. Their presentations will be followed by a brief Q&A session. Then Mr. Neth Walker will discuss the application of remote temperature monitoring to quantify natural source zone depletion, or NSZD, rates at 2 DoD sites impacted by NAPL. Neth's presentation will also be followed by a brief Q&A session, and we will conclude the webinar with a longer Q&A featuring all of our speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you may view the slides using a compatible internet browser, such as Firefox, IE, or Edge, and by creating a free Zoom account. If you're unable to view the slides or if your screen freezes, just try keying in Control and F5 to perform a hard refresh of your screen. If you happen to be accessing the audio through your computer, click the arrow next to the Join Audio button, select the speaker and microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, just call into the conference line shown here. You can also submit a comment using the chat box at the bottom of your screen. Just use your chat box only for comments related to technical difficulties, because the Q&A option should be reserved for questions for the speakers. And in case you continue to have technical difficulties, just download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Keep in mind that we will be live streaming the webinar on the StartUP and ESTCP YouTube channel, and that link is shown here. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit them well in advance of the Q&A sessions. And when you submit your question, please add your organization name at the end of the question so that we can identify it during the Q&A. The next few slides will provide a quick overview of StartUP and ESTCP. StartUP is a strategic environmental research and development program. It was established in '91 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. StartUP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. StartUP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program, in which innovative environmental and energy technologies are demonstrated. ESTCP investments capitalize on past investments under StartUP or other research programs, and they're designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. StartUP and ESTCP are complementary programs, with much of the StartUP research occurring at the lab or pilot scale, with occasional field efforts, while ESTCP demonstrations are primarily at the pilot, and feed scale, although occasionally supporting lab efforts are conducted. There are several environmental drivers for the type of work funded by both programs, with the underlying objective of sustaining DoD ranges, facilities, and operations. This is a broad undertaking. It takes the form of looking at maritime sustainability, threatened and endangered species, climate impacts, unexploded ordnance and munitions constituents, as well as other environmental drivers. One key environmental driver is the reduction of current and future environmental liabilities. This involves addressing contamination from past practices, including impacts to groundwater, soils, and sediments, UXO contamination, and developing management approaches for contaminants of emerging concern. The second part of this is pollution prevention, with a focus on eliminating chemicals of concern or hazardous materials in manufacturing, maintenance, and operations on military installations. There are several main focus areas for research and demonstration at SERDP and ESTCP, and these are shown here. And as mentioned earlier, technology transfer is very important within both programs. It includes the development of videos, training workshops, and guidance documents. The webinar series is a substantial component of StartUP and ESTCP's technology transfer efforts. The webinar series highlights research and demonstration efforts from all of the StartUP and ESTCP program areas. Upcoming topics, as you can see, include PFAS leaching and mobility at AFFF impacted sites, ecosystem model comparison, environmentally sustainable methods to remove AFFF from firefighting delivery systems, and others. Registration is free and is open for webinars through the end of this year. You can find additional information about upcoming webinars at this link. Note that all past webinars are archived and can be accessed using this link. So you'll be able to find webinars from as early as 2014 on this website. And you can download a copy of the presentations and view the videos of such webinars. And for today's event, just a reminder that you can download a copy of the PDF on the webinar webpage as soon as now, and a video will be available in about a week. It is now my pleasure to introduce the speakers for the first presentation. We have three speakers. Dr. Bo Stewart is the Vice President of Praxis Environmental Technologies in California. He has over 35 years of experience in applied research related to environmental restoration, and that includes technology development, technology testing and evaluation, and remedial design. Bo is a registered mechanical engineer in California. He received a bachelor's degree from North Carolina State University, a master's degree from the Georgia Institute of Technology, and a doctoral degree from the University of California, Berkeley, all in mechanical engineering. Dr. Mark Woodison is a professor and department head of the Charles Villa Jr. Department of Civil and Environmental Engineering at Virginia Tech. Mark's research activities include studying the fate and transport of chemicals of concern in groundwater systems, remediation of subsurface contamination, and groundwater resource management. Mark is the author of several software tools, including Seam3D and NAS, which are used to evaluate remedial strategies to address site remediation objectives in conjunction with economic and risk management assessment models. Mark is a registered professional engineer in South Carolina. He received a bachelor's degree in civil engineering from the University of Cincinnati, a master's degree in water resources engineering from the University of Kansas, and a doctoral degree in civil engineering from Auburn University. And finally, Dr. Mike Cavanaugh is a senior consultant with Geosyntac, also in Oakland, California. Mike has co-authored more than 40 peer-reviewed technical papers and has edited and contributed to 6 books on water quality, water treatment, groundwater remediation, and aquifer restoration. Mike was elected to the National Academy of Engineering in 1998 for his numerous contributions to water quality management and the remediation of contaminated sites. He earned bachelor's and master's degrees in chemical engineering from Stanford and the University of California, Berkeley, respectively. And he also earned a degree in civil and environmental engineering from Berkeley. Mike, please get us started with today's webinar.
Thank you very much, Arula. It's a pleasure to be here, and good day and good afternoon to all of our participants. Next slide. We'd like to cover a number of topics today regarding this particular project, and I wanted to start with the first, which is our project motivation. Next slide, please. I think everyone on the call recognizes that over the past several decades, there's been much success in remediating DNAPL or NAPL sites, and there's been considerable research on how to address the issues, this difficult technical issues in dealing with NAPL, both in the DNAPL form and the LNAPL form. The cost to complete in the installation and restoration program is dominated by about 500 sites with estimated costs exceeding 10 million. Many of these sites have residual NAPL. This raises the need for continuing development of tools to assess transition options to less costly long-term management, as pointed out in the 2013 NRC report on this topic related to the issue of transitioning many of these difficult sites to some alternative state. This requires the development of the desire of the project was to develop some simple tools that describe very complex processes, but in a way that is providing sufficient accuracy of these modeling efforts that can lead to long-term decision-making in the transition process. This tool should be accessible to everyday practitioners and managers, and something that would lead to guidance for enhanced site characterization to determine which parameters should be measured. And we think it also can be used ultimately in the value of information analysis, predicting supporting the need for and the cost for additional site characterization. Next slide. To put this in graphical form and visual terms, we know that we have numerous numerical models, phase transport models, multi-phase models that can provide an estimate of the mass discharge coming off of a source. It's a complex calculation, requires considerable effort, time-consuming, costly, and often there's a lack of data. On the other extreme, we have numerous screening models that are available, but these models often are based on an incorrect or a oversimplified physical model. For example, the REMChlor model based on the gamma function showing the depletion function as a function of this one parameter gamma. In contrast, we propose a volume average model that can be applied in the context of applying known mass transfer concepts to transport in the subsurface, in the saturated zone, to undertake an analysis of the dissolution and phase transport of NAPL components, regardless of the architecture of the NAPL, whether it's in a ganglia or pool form. And this will lead to a more rapid estimate of the mass discharge coming off of a site that can then be used in evaluating alternative remedial decisions. With that, I'd like to turn it over to Bo to talk about how we developed this methodology.
Thanks, Mike. I'm going to cover the modeling approach, in essence, to give you a high-level view of what goes into the model. Then we'll cover the input parameters. There aren't that many, but they're very important. So it's very important to estimate them as well as you can. And then after that, I'll present the results of a demo where we were supporting the remedial decision. But you could also, and we demoed the use of the modeling for doing remedial performance evaluation at a site that was complete. So let's first look at the modeling. And as Mike said, we're looking at a volume average source zone. So what that means is, if we look at this dashed box, all of the NAPL source material is within that box. And we look at simplified flow through the box. So really, we'll call it a characteristic flow or an average flow. And what this does is eliminate the need for a discretized numerical model. So we're just looking at a characteristic flow. And that eliminates a lot of the sort of computational difficulties, and that's where the major simplification occurs. Then we add in remedial technologies. The modeling is really applicable to sites where you've exhausted the recovery of mobile NAPL. So in essence, what you're doing is enhancing the dissolution rate. So when we say enhancement, we can't, that's defined by some base case of dissolution. And that's the focus of our work, was what's a good process model for that dissolution? And then the outcome of this would be the contaminant mass discharge. And that would be the input to, say, other transport models to evaluate the plume. So our modeling doesn't look at the plume itself down gradient. We're just looking at the source zone and how to handle that. And what you end up with the one-dimensional flow is a system of first-order equations that's readily solved. And so, even with the spreadsheet models, and we have different scenarios we look at, and our modeling is under the moniker of source control and remedial performance evaluation. So we've developed SCARP-A tools. So let's look briefly at what we're talking about with NAPL dissolution. So we have sub-NAPL, D-NAPL in the subsurface. And when it's released, we generally look at two types of architecture. It moves down through the soil, leaving behind disconnected blobs that are immobile, but they're at a low saturation and you have good flow through that zone. Then they might hit some permeability contrast and collect at a high saturation and spread laterally, versus vertically here, and now we're going laterally, and you have a high saturation, so the flow generally bypasses over the top. And traditionally, we have the mass transfer coefficient here. This is the mass discharge rate, mass over time coming out of the source zone. And we try to quantify that. We know it's at disequilibrium with a mass transfer coefficient. And with numerical modeling, when you get down to cells, you're trying to look at these two very different scenarios with the same K. And we've looked at a process model, or developed a process model to bring those together and have that published. All right, so once we developed the model, we then validated it with application to a number of experiments of dissolution and with remediation. And what I'm showing here is an experiment from Arizona State University, where again, we have our source zone, and then we can have NAPL architecture. And I show the two basic cases, but the modeling is applicable to multiple, the more you know about the site. But they had a nice experiment where they released it at the top, pulled at the bottom. And then you can see this is associated with that ganglia column, where it depleted quickly because you had flow through with a lot of surface area. And then you had flow over the top of the pool, which persisted for a long time. And you can see even in this trend, long-term trend, it's difficult to say when that's going to end if you're only looking at the data here. So pools really govern the lifetime of an NAPL site. And our modeling includes back diffusion as a first order process, the classic approach to it. But in terms of the lifetime of the source zone, that's going to be a small contribution. And as a result of our work, I'm bringing this in early, that we have two tools available at this point. These are beta versions for you to evaluate and tell us how we can improve. We have one for a single component NAPL, which considers more complex scenarios of multiple NAPL, but it's single component, but no, you can have multiple pools and ganglia within that model. And then we have a multi-component NAPL solution, which can be run in a spreadsheet. But in this case, we're only looking at a single architectural feature, such as either a ganglia or a pool. And we'll look at that when we get to the demonstration. And those are available for download at scarpamodel.com. So what I haven't talked about yet is how we handle the modeling of the remedy itself. And as I said, we're looking at sites where the NAPL has become immobile. You have a residual phase, and we bring in this enhancement factor. And that's traditionally the way it's done in the published literature and in the research. But what they don't have a very good handle on in the past has been on this mass transfer coefficient. So what is being enhanced? So if you can imagine pumping through the site, you're enhancing it just by the increased flow rate. And if you added a surfactant or a surfactant, you increase the solubility. You know, we're looking at surfactants that increase the effective solubility, not mobilization. And that's the more typical, is to look at enhanced solubility. And then a little bit more difficult term looking at is the dissolution rate is driven by a concentration gradient between the NAPL interface and the bulk water flow. And when you have reactions that are eliminating the contaminant from the aqueous phase, that concentration gradient gets larger. So the faster your reaction rate, the larger that driving concentration gradient, the greater the enhancement. And we'll talk about this a little bit more in the site demonstration. So as you can see, I mean, with all models, the data that you input is what's important. So we're going to go over, you're only as good in your results as what you put into the model. So a key component would be the groundwater velocity, and that's generally available at almost all, well, it should be available at all sites. And then down gradient at NAPL sites, we typically look at a mass flux or a mass release rate, and we define some, I guess, flow plane that it's moving through either, you know, transects of multi-level samplers or other monitoring wells. And then somewhat also from direct push technology, and that's looking outside the source zone. But another key parameter would be the length of this source zone, and that typically is even a little bit harder to estimate, because now you're looking at going into the source zone and poking a number of holes. Where does the NAPL start in the direction of flow, and where does it end? All right, so then we've defined our box, our source zone on the outside. Now we need to define what's inside, and we can get that data. I mean, for each of the masses inside, the better we can define it, the better our results again. But we need to know these dimensions, the height, width, and length, at least some estimate, a characteristic of it. Not the precise number, just a characteristic number for it, and also with the pool. And then we have literature to guide us on what typical saturations would be when, you know, looking at boring logs, and we can get an idea of, yeah, this looks like it's going to be ganglia, it's in a sand, versus a pool where we were going to see at an interface, we can expect the saturation to say be on the order of 20, 30, 40% of the pore space being occupied by the NAPL. Then we put all of this together in the model. That's basically the input that I've gone through. Now, how good are your results? So as I said before, we generally have an estimate for the total mass discharge from the site, or we have a mass recovery rate from pump and treat to look at. And then as we get more data, we're adaptable. This brings all of the large scale data, small scale data together. And then our guidance document on the user manual describes all of this. We have it all tabulated for the input data and where you can go about getting it and estimating it. And our final report has good examples of how to do that. So let's move on to the demonstration for remedial decision. This is at the former site. This is an ongoing site, site ST-12 at former Williams Air Force Base, where they've released, they had over 2 million gallons of jet fuel released primarily in the 70s and the 80s. The water table, I mean, at the time of that release, there's all these zones that it's gone through, the water table was down at 230 feet at that time, and there was primarily, it was pooled atop that. There were several feet thick of NAPL pool at 230 feet. So this was a very challenging site. But over the last 30 years, the water table has come up about 90 feet and left behind all of these strung out pools. Our NAPL is now a DNAPL, trapped underneath fine-grained units. And over this 30 years, they've applied pump and treat, monitored natural attenuation studies. They've applied full-scale steam enhanced extraction. And still, the site has not been remediated. So our objective was, what's the sort of support the decision on the best remedial path to move forward with. And a little bit more about the site. This purple dashed line was that pool of NAPL sitting at 230 feet around 1990. And this is well over 1,000 feet, 1,200, 1,500 feet across. And it takes 10 to 12 years for the groundwater to move across it. The red dashed line is where steam was applied in 2014 to 16. And these purple circles are monitoring wells where NAPL could be recovered even after the steam treatment. The difference being inside the zone, the benzene was fairly well depleted. Outside, not much change in the NAPL. The green contour is our current estimate of MCL, and it lines up pretty well with that NAPL pool from 30 years ago. So, but the bottom line is there's still NAPL all around the edges. So after 30 years and tens of millions of dollars of remedial effort, we're still haven't really reduced the time frame of remediation at the site. We reduced the mass flux, but the site period it will be there has not been reduced. All right. So in building our conceptual models for the site, again, we were looking for characteristic dimensions and saturations. We went through 30, well, more than that, 40, 50, 60 boring logs and looked at where they detected NAPL in dye testing and compared that with the geology and came up with characteristic dimensions and saturations for 6 areas around where they had done the former steam treatment. And put that into the modeling, the approach. But before we talk about the model results, you can look at sort of 2 extreme scenarios where you would have a pool at a 30% saturation over some area, or there could be ganglia over a large column if you were just looking at this blindly and just assumed you had the same NAPL mass. And these would behave very differently, as we showed in the experiment. And we'll talk about how you can assess that with uncertainty again on another slide. But let's get back to the results for this demo. And we use the Excel tool that you can download from the website. The yellow data is the required input for the modeling. Again, these were the characteristic dimensions and saturation, well, the characteristic dimensions and flow through the source zone, the dimensions and saturation in the for each of those NAPL masses, individual masses. And again, we only looked at one here. Single component model, you can put up to 10 masses inside. And then very simple input for the remediation. So, and then the purple here is it immediately gives you an estimate for how long that source zone would be there for different, assumptions on the remediation. So let's look at the results at this site. So I'll turn first the enhancement factor. We looked at, looking at natural attenuation. You have degradation occurring naturally, and it roughly on the order of 1.5 times faster than you would remediate with just water flowing through. So the bio is contributing to enhancing the dissolution. Then you can enhance the bioremediation. They're looking at sulfate reduction at the site, adding sulfate. Maybe you can triple the dissolution rate. There's a slow groundwater velocity at the site. So you could, on the order of increase the dissolution by an order of magnitude by pumping pretty hard at the site. And even over that large area that I showed, we're talking about this factor of 10. We considered it, from more practical terms, on the order of maybe 300 gallons per minute. And then we looked at ISCO as increasing that concentration gradient. So the closer the oxidant can get to the NAPL, it reacts in the aqueous phase. We tried to be a little conservative from, say, theoretical estimates might be 30, but more like 15 in the modeling. And the outcome of that is that, you know, with natural attenuation, and this is consistent, the pools would be there for centuries. The ganglia would go away faster, zones. We left those in for comparison. And it follows along pretty well with the enhancement. So that's why the enhancement is important to estimate as well as you can. And we've got a lot of guidance on that. Then that's included as a tab in the spreadsheet, methods for estimating that. But you can get down to you know, a century, but you have to be actively pursuing that, or pumping for 30 years, or actively implementing ISCO for a decade. And these provide the input for, you know, feasibility studies and cost evaluations that are ongoing at the site. The remedial project managers are giving me good feedback on that. And the modeling can be done, you know, tabletop and real-time changes and see the results. But we also connected it, not in the downloaded version, but to PEST, where you can do an uncertainty analysis and get a better idea of, well, if you put a bound on each one of those parameters, there aren't that many. What is the lowest value I think I'll have? What is the highest value? We did that for all of the parameters, put it into an uncertainty analysis, and came out with, okay, well, we were a little pessimistic. Our best estimates for natural attenuation had us out around 300. The uncertainty analysis says maybe it's 200. That's some improvement. But what the main result of this is that it did support these estimates for the different remedial technologies. And so it was very straightforward. You know, numerical models take a long time to perform that type of calculation. These execute quickly because the model executes quickly. So in conclusion, on, you know, sort of the model description, volume averaging is straightforward for the complex processes. It's easy to solve. You can do it yourself. I mean, we have described the methods in the final report. The conceptual model are adaptable. So the modeling is easily adapted to more data that you have of the site. And it can guide you, like we said in the beginning, on site characterization, even from the uncertainty analysis, what should be looking at. The framework provides you to be consistent in how you evaluate your remedial technology. Same conceptual site model. Well, we already knew that the pools were going to be dominant. We have 2 simple beta version tools available, but you can see how this could become more complex. And at this point, I'm going to turn it over to Dr. Widdowson to talk about the next steps and the benefits to DoD.
Great, thanks, Bo. Let's start with those next steps in the next slide. So as Bo described, the intended use of this volume averaged model is through the Excel tool. And we're working, though, on incorporating this approach into the numerical transport model SEAM3D, which is available in the GMS platform. This would function as an additional modeling package for source zones, similar to the SEAM3D NAPL dissolution package. And this would enable us to then simulate plume dissipation with SEAM3D in conjunction with the volume averaged model. I think the advantage here is that this would leverage existing site models and provide similar capabilities to complex models for multi-phase dissolution. We're working on expanding the tool capabilities for additional technologies for source zone remediation. We're looking at emerging contaminants, of course, including PFAS compounds, incorporating that into the tool. We've already shown some promising results using statistical tools to evaluate the uncertainty of input parameters and also the sensitivity of output. So looking now at the benefits to the Department of Defense, and starting really going full circle to Mike's opening comments, obviously complex sites with NAPL source zones are going to be costly to remediate and to address. So this tool is designed to improve decision-making in looking at source control options and then transitioning to less costly long-term management strategies. The tool can be used to optimize additional data collection at sites to improve application. And we wanted the tool to be scientifically defensible. So it's based on mass balance and well-established mass transfer models, and it's now validated at field sites. We purposefully designed the tool to facilitate dialogue among stakeholder groups, so you can answer what ifs in real time in an accurate and efficient technology. We also purposefully designed the tool for consistency in application over time at a site and among sites. So looking now at the next slide, we have a list of additional resources, the website to download the model. Of course, the final report will be published on the ESTCP website. We've listed a few of the publications, including one already published in the Journal of Contaminant Hydrology that describe the tool and its application, as well as some of the uncertainty analysis. So on this last slide, we have our contact information, including the link to the website for the final report, and we would be glad to take any questions.
Great, thank you so much to the three of you for a fantastic presentation. Just a reminder for those that want to ask questions, please get them into the Q&A box at the bottom of your screen. For this team, we did receive several questions. The first one is from the US Navy. How applicable would this methodology be for non-sedimentary units like fractured bedrock? Bo?
Yes, so that's almost, I mean, we put in, it would be applicable, but we would, the transport, the math would be different. I mean, it looks like with fractured rock, you have dual porosity. We could adapt to that, yes, but it's not in there now. The flow modeling, it would add another mass transfer coefficient having to do with the fractures.
Great. Mark, anything you'd like to add before we move on to the next question?
Yeah, I think it's a great question. We at this point, we've limited our validation application to really unconsolidated sediments. But as Bo pointed out, and I think one of the advantages of this tool is the ability to adapt the tool is one of the pluses of this tool. And so we could make modifications as needed, and that's now on our list for next steps. Thank you.
Wonderful. This next question is as follows. What happens when you have both NAPL in the localized source zone and in the remote plume? Do you just make your volume average box bigger?
Well, you would treat them separately. So, so what would happen, depending on how remote they are, you could connect them with the transport model. So you would have a mass release rate from, say, your primary upgradient NAPL zone. So that discharge would need to be transported down gradient. And that would provide a new, we allow for non-zero input contaminant concentrations into, say, the second down gradient zone. Hopefully that answered the question. It's a little
Great,
more
thank you.
complex, but it's certainly the approach would work there.
Thank you. Does the tool provide guidance on selecting representative source degradation rates for natural attenuation or active remedial approaches?
Well, I'll say the tool doesn't, and I'll defer to Mark for all the tools that do. That's his expertise.
Mark?
Yes, I'm here. Sorry. Yeah, I would say that the advantage here is that the input parameters are fairly straightforward to apply. They're going to be very site specific. And then in terms of, guidance on mass transfer coefficients, we're building that into the tool itself.
But I mean, as far as the first order rate estimate, I mean, there are plenty of tools available. I think GSI, Neff may speak to that in his talk, has tools for estimating first order degradation rates for the biological. And I think you're working on that on projects as well, Mark. Anyway.
All right, so while LNAPL pools are common, how common are DNAPL pools, and how well does this approach simulate DNAPL mass transfer?
Oh, yeah, we gave the example site, was LNAPL, but it became pooled. It was an inverted DNAPL, but the models were developed more specifically for DNAPL. So that's the target. And we have a demonstration within the project that was to a DNAPL site in looking at performance evaluation of the remedies that they did apply. Great,
thank you. Have you done sensitivity analyses on remediation timeframes?
Yes, and that was the focus. One of the papers we listed that's with water resource research right now was sensitivity analysis of the model parameters.
All right, the next question is from a government contractor. Does the tool allow for customizable decay rates?
The tools that are available do not. I mean, these are beta versions that sort of implement the simplest approach. These complexities can be, you could use MathCAD or come to us, and we can put together, a system of first order equations that you can solve that would do that.
Great, thank you. This question is for Mark from the US Navy. You mentioned that you were intending to utilize this model for PFAS or other chemicals of concern. When the chemical of concern is not an LNAPL, how does the tool treat transport? As LNAPL and non-LNAPL transport is very different, even if the subsurface environment is the same. Do you have to create a separate model for each chemical?
Right. So what our thinking of this, again, this is a source zone model, and the source itself, it can be a NAPL, it can be an LNAPL, it can be a DNAPL. And when it comes to other contaminants of concern, they may not be present in a NAPL phase. Our thinking here is that the tool has application to really a range of compounds that would be present in the source zone that could be then emanating and coming out through desorption, back diffusion, or a combination of this mass transfer processes. And so, but you can have a multi-component source. And so our intention then is to be much more explicit and to incorporate long-term some of the mass transfer models that would be applicable to PFAS compounds.
Great, thank you. And another question from the U.S. Navy. What is the range of remediation timeframes, and what are the most sensitive parameters in the model?
Well,
Bo, would you like to take a crack at this?
Well, I'll take a crack. Yeah, I mean, the range is, it's very site specific. You know, the architecture and really the input parameters. I mean, if you have some idea of the extent of your, if you had a NAPL pool, the extent of it, you can estimate the saturation and get an idea of, and look at your groundwater velocity. I mean, you can get a pretty quick estimate of how long it will be there. And that was, you know, we did that in the sensitivity study that hopefully will be published soon. But you can also find the results of that in the final report. It's very site specific to say, you know, what the range is.
Okay, thank you for that. And as we wrap up and before we transition to our last presentation today, Mark, can you tell us if this software is free for public use?
Yes, it is free and it's downloadable from the website. And as we make improvements and any changes to the software, we'll add those to the website. That would allow people to take advantage of any improvements that we've made.
Great. Well, thank you to all three of you. We will get back to any unanswered questions depending on how we're doing as far as time at the end of the webinar. But for now, we're going to go ahead and transition and introduce the speaker for today's second presentation. Ness Walker is a senior geologist and engineer with GSI in Houston, Texas. He has over 11 years of experience in the environmental field and has performed environmental site assessments and provided remediation support at numerous facilities across the United States. Ness was a key developer of the thermal natural source zone depletion dashboard and has designed and implemented thermal monitoring hardware for NSDD at NAPL sites. Ness is a registered PE in Texas and California and a registered PG in Texas and Alabama. He received a bachelor's degree in geology from Washington and Lee University and a master's degree in civil and environmental engineering from Stanford. Ness, please get started.
Thank you, Rula. As Rula mentioned, I'm Ness Walker with GSI Environmental in Houston. Today, I'll be talking to you about remote monitoring of natural source zone depletion using temperature data to support long-term passive management strategies. This is an ESTCP project that we're wrapping up. Tom McHugh, my colleague, is the PI. We should be submitting our final report here within the next week or so hopefully that'll be available on the ESTCP website. But we have completed all of our data analyses, and so what we will be presenting today are our final results. So today I want to start off by discussing natural source zone depletion, then move to our project objectives for our ESTCP project, and then focus on three key tasks. One is to look at a multi-site NSED plumathon style study, and then present the results from two demonstration sites, the first in Utah and the second in Minnesota, but before moving on to conclusions and then benefits to the Department of Defense. So when we talk about natural source zone depletion, what do we mean? So natural source zone depletion, or NSED, it's a combination of processes that reduce the mass of the NAPL in the subsurface via processes including dissolution, volatilization, and biodegradation, with most of that taking place via biodegradation. So here on the left, you can see our typical conceptual model where we have in brown this mobile or residual NAPL body. We like to think about that as floating on groundwater. And we've long recognized that some of that mass dissolves into groundwater. We get these dissolved phase plumes like benzene plumes or BTEX plumes. And this led to a lot of work in the 90s and early 2000s with monitored natural attenuation. And over the last 10 to 15 years, we've recognized as a scientific community that much of that mass actually doesn't go into the dissolved phase, but it moves up in the vapor phase, typically 90% or more of that mass. And so we have this anaerobic biodegradation process of the NAPL itself that releases carbon dioxide and methane. At the same time, we have oxygen that's diffusing down from the ground surface. And where that methane and oxygen meet, we typically find this aerobic methane oxidation process. This is an exothermic process, so it releases heat while also converting that methane to carbon dioxide. And this gives us two signals that we can really clue in on to try to measure the NSED rates. The first is going to be the carbon dioxide flux at the ground surface. The second is to try to measure this heat signal via temperature sensors like thermocouples to back out what that NAPL degradation rate is, or NSED rate. So based on work that we've done and many others have done over the last 10 years, we found that measured NSED rates are often in the hundreds to thousands of gallons per acre per year. And this gives us a yardstick to compare to other technologies, like an active technology. And if you think to a late stage recovery system may only be removing a few gallons or tens of gallons of acre per year, this gives us something to compare with just based on those natural processes. So there are four commonly applied measuring methods to measure NSED rates in the literature. These are described more in ITRC's NAPL 3 guidance document from 2018, as well as a recently released ASTM standard that was published in December of 2022. And so carbon traps measure the CO2 flux at the ground surface. Typically, these are a short-term integrated signal. They're deployed for a couple weeks, whereas dynamic closed chamber, or DCC, sometimes referred to as LICOR, they measure the instantaneous CO2 flux at the ground surface. If you install a vertical series of soil gas vapor monitoring points, you can look at the gradients of your methane, your oxygen, and your carbon dioxide and apply the gradient method to get NSED rates. And then finally, you can install a vertical series of thermocouples or temperature sensors and use that to measure NSED rates. So in our ESTCP project, we really did focus on the temperature-based methods. And so let's walk through that here. Again, on the left, we have this conceptual model of what's taking place. We install a vertical series of temperature sensors in the subsurface. And because of that aerobic methane oxidation front that's releasing heat, we can try to measure that. So if we take the background corrected temperature signal, so here we've removed all of our non-biogenic sources of heat, things like solar insolation, and so we're only left with the temperature signal from biodegradation. We typically see the shark fin, this peak temperature differential at the methane oxidation depth. And using Fourier's law, we can measure the heat flux to the ground surface as well as heat flux to groundwater. We can then use that heat flux and using stoichiometry and thermodynamics, use that to calculate the methane oxidation rate, which in turn we can use to calculate the NAPL degradation rate. And so if you think about a gallon of, say, gasoline, the amount of heat that it releases in the subsurface is going to be the same as it would release as if you just burned it in an oven. And so we're able to take advantage of that heat. And so the key point is that we can use that heat flux from our vertical temperature profile to calculate our NSED rate. So the technical objectives of this project were to demonstrate the use of temperature-based methods to accurately measure those NSED rates, typically expressed in gallons of NAPL degraded per acre per year in the NAPL source areas. And so the thermal methods in general have been well validated as well as the other methods. And so this project really sought to find better ways to improve upon the work that had been done. And the first of those is to advance improvements to the background correction, right? So figure out better ways to remove that non-biogenic heat signal so we're just clued in to what the bacteria themselves are doing. The second is to demonstrate new second-generation field hardware using cheaper Internet of Things or IoT sensors to provide better and more temperature data at lower cost than some of the earlier applications. And the third is to validate the application of the temperature methods below paved surfaces, so things like tarmacs and large parking lots and other paved areas, which are very common at DoD facilities. Do these methods work underneath the paved surfaces? And then finally, explore the processes that are governing these NSED rates via a multi-study NSED plumathon study. So that's what I want to talk about here first to set the stage for our demonstration project. So we went out into the literature. We found all the published literature with NSCD rates that we could, and this gave us a data set of 40 sites. And at those 40 sites, most of which are in the United States, a few in Australia, we computed an average site-wide NSCD rate. And so what we found is that all the sites that had studied NSCD had measurable rates, with 90% of those sites greater than 170 gallons per acre per year, with the median site around 1,000 gallons per acre per year, which is around 9,500 liters per hectare per year. And the sort of second question is, what are some of those factors? And so it's been hypothesized that lighter, shorter chain hydrocarbons like a gasoline may degrade faster than some of the heavier or more complex hydrocarbons. And so we looked at the fuel type at each of those 40 sites, and with the exception of fuel grade ethanol at 2 sites, what we found was that the fuel type is not a primary driver of NSCD rates. There's no statistical difference in the NSCD rates amongst the various types of fuel. And so that indicates that there are other site-specific factors that have more of an impact. And we did try to parse some of those out, whether it's climate, hydrostratigraphy, depth of groundwater. But unfortunately, in our data set, there wasn't enough detail in the published literature to do a robust statistical evaluation of what those other factors actually are. Another thing that we did with this data study was we took all of the studies that had published NSCD rates from multiple methods, and then we compared those. And so here what we're doing is we're taking the ratio of a given method and we're comparing that to any other method. And that's what you see here on this log scale, these dots. And so what we found was that site-wide NSCD rates did vary with measurement method, but no one method had a statistically significant high or low bias. And almost all of these ranges were within an order of magnitude. And about half that data was within a factor of about 3 to 5. And what this suggests to us is that any of these methods are valid if properly applied at a site. And then choosing any one of these methods should give you the true NSCD rate within a factor of about 3 to 5. Now moving, so a question is, we have all this data from these 40 sites, why do we need to go to 2 more? And so much of the published literature really focuses on unpaved surfaces. And so this project really sought out sites with NSCD below paved surfaces. And so we evaluated this by installing 5 NSCD monitoring stations, 3 in paved areas, 2 in unpaved areas, 3 in impacted locations, 2 in unimpacted. And so for the paved areas, we installed 2 sensor stations within the impacted zone with 1 corresponding paved location. And then as a comparison, we also installed an impacted unpaved location as well as an unimpacted background unpaved location. At each of these 5 sites, we installed 3 types of sensors to evaluate 3 primary NSCD lines of evidence. The first were soil gas profiles. And so in the lower left corner, we have this plot of gas concentration on the x-axis, the depth on the y-axis. And what you would expect to see is that oxygen decreases with depth and carbon dioxide and methane increase with depth when you have NSCD taking place. We also installed the temperature profiles. You can see here this profile of background corrected temperature. And so we're looking for temperatures above background, and then we're looking for this shark fin type peak at the methane oxidation front. And then finally, we deployed carbon traps for a couple-week period at the beginning of our field deployment period. We went to 2 sites. The first was the Tooele Army Depot South site, south of Tooele, Utah. This is a fairly well-characterized site. There's been active remediation. It's an older spill. And then we went to the Minnesota Air National Guard facility, which is adjacent to the Minneapolis International Airport. This has been a more recently discovered spill. There's been no active remediation, and they're currently undergoing site investigation activities at that facility, which is something we'll want to keep in mind as we discuss the results. And so now I'm going to walk through the results first at the Utah site and then at the Minnesota site. Here we have a site map. In yellow, you can see the assumed NAPL extent. The background locations are in purple. The impacted locations are in pink. The paved locations are these triangles. the unpaved, or these circles. And so this diagram presents the qualitative results from carbon traps. And what we found was there was no evidence of NSCD at either of the two background locations, which is not surprising for this well-characterized site. We found some evidence of NSCD underneath the paved surfaces. We measured NSCD rates with carbon traps, but they were relatively low rates. And then we had a much higher rate here at L3 at an unpaved location. If we switch and look at the soil gas profiles that were installed, again, we're looking for a decrease in oxygen and an increase in carbon dioxide and methane at these locations if there is an SED. We can see the paved locations here on the left, the unpaved on the right. We have the impacted locations up top and the background locations below. And each of these lines is a different measurement period. We went out at the Utah site 3 different times, separated by about a year each, and collected soil gas profiles. And so at the impacted locations, you can see that the concentration profiles match our theory of decreasing oxygen, increasing carbon dioxide and methane. But when you look below at the background locations, we're not seeing those changes. And so those soil gas measurements at the Utah site follow our conceptual model, and that they indicate NSCD processes at the 3 impacted locations. Now, if we plot the mean annual vertical temperature profile, so here both of these plots show our annual average temperature on the x-axis, depth on the y-axis. And so the theory here is if you look at a year's worth of data, in the absence of any biogenic processes, you'd expect a vertical profile, right? The summer heating would balance out the winter cooling, and you would see no change in temperature with depth. And if you looked at the paved locations, that's more or less what we're seeing. Our two impacted sites here in the green and the orange match the blue background. There's no apparent temperature difference. There's no apparent shark fin. But if you look on the right at the unpaved location, you can see here how the impacted location in orange is 1 to 3 degrees Celsius warmer than its corresponding background location. And there appears to be this peak at around 8 feet below ground surface. So if we look at all of the qualitative evidence from these 3 different methods, they're all in fairly good agreement amongst all of them. The only exception to that is the temperature profiles at the paved location. There was very little evidence of NSCD, but we did see some evidence with both the carbon traps and the gradient method. Now, when we look at actual calculated NSCD rates, so for the temperature-based thermal methods, we apply 3 different approaches. One is to take that annual average temperature, so using a year's worth of data, and calculating our fluxes off that corresponding gradients. The second is to do a background correction, where for every day we take the temperatures at our impacted locations and we subtract out the corresponding temperatures from our background locations. And this allows us to calculate NSCD rates on a daily basis. And then finally, we have this novel single stick algorithm that were developed by Drs. Kaywan Karimi Askarani and Tom Sale with Colorado State University. This uses an algorithmic approach to remove the non-biogenic heat signal at each station, just using data from that station. And then on the far right, we're comparing with our measured NSCD rates from carbon traps. And what we find is generally good agreement between all 4 of these methods within a factor of about 3 to 5, which is consistent with our NSCD Plumathon study. It is noteworthy, again, going back to the prior slide, that at the 2 paved locations, it's a lot harder to resolve those NSCD rates when there's just not much NSCD going on. And so the noise in the signal makes it really hard to resolve those rates. But at the unpaved location, you can see it's a little bit easier because there's more NSCD going on, and that's consistent amongst all of the methods. Switching gears here to our Minnesota site, again in yellow, you see the assumed NAPL extent. At both background locations, we did see some weak evidence of NSCD based on our carbon trap results, so low levels of petroleum hydrocarbons. We saw, again, a little bit of weak evidence at the unpaved location, and then fairly strong evidence, much higher rates at our 2 paved locations at this facility. And again, this is the facility that's still undergoing site investigation activities. If we look at our soil gas profiles, again, at the paved locations, L2 and L3 on the right, we do see that decrease in oxygen, increase in particular in the carbon dioxide, Whereas when you looked at the unpaved impacted location and the two background locations, we really don't see those decreases except in one event. In Minnesota, we took 2 different rounds of these soil vapor profiles, hence the number of lines. And so the soil gas measurements follow our conceptual model and indicate NSED at the 2 paved locations, but not really at the unpaved or the background locations. And then finally, looking at the mean annual vertical temperature profiles, on the left at our paved locations, we see a pretty good separation. So 2 to 3 degrees Celsius warmer temperatures at L2 and L3 there in the orange and the green relative to blue with what appears to be a peak around 2 to 6 feet below ground surface. But again, looking at that unpaved location, we don't see any evidence based on the temperature signal. There's no separation in the temperatures and there's no apparent peak in the subsurface. So again, when we compare these qualitative lines of evidence, we get fairly good agreement. Again, I want to point out at the background locations, there was some weak evidence of NSED, suggesting that there may be some poor site investigation activities, or at least not enough for when we went out and installed this equipment. And then calculating NSED rates again with the same approach below. Again, we're finding pretty good correspondence and rates amongst the various methods. Again, with a factor of about 2 to 3, usually a little bit better here. So again, in general agreement with what we found with our NSED plumathon study. And again, we did find measurable rates at the 2 background locations. So to wrap up, if we go back to our original technical objectives, what did we find? And so we set out to advance improvements to background correction, but we find that background correction for evaluating NSED rates still is a challenge. And I think there's still work to be done here on that background correction to remove all of those non-biogenic heat sources. The second was to demonstrate new 2nd generation field hardware that provides better temperature data at lower cost. We did get a lot more temperature data. We were able to install 16 to 20 temperature sensors at each location, but data connectivity and recovery challenges remained. We had almost perfect data recovery at Utah, but at our Minnesota site, several of the locations really struggled to transmit data over a cell signal. And so one of our key findings is that it's really important to have a local data backup. So in addition to trying to rely on the cell signal, make sure that all of that data is also being recovered locally so that you can always send out somebody to the field and recover that data if necessary. The third is to validate the application of the method below paved surfaces. In general, we found that NSED rates were successfully measured below paved surfaces, but some site-specific issues may be present. We saw that again at the Utah site where we had much lower NSED rates under the paved surfaces. Also want to point your attention, there was a paper published in 2021 by Jonathan Smith and his colleagues. They looked at a paved retail fuel station in Italy as part of the Kakaway project, and they too found measurable NSED rates. And so, the evidence is that NSED is occurring below these paved surfaces, and that we can in fact measure those rates. And then finally, we're exploring processes governing NSED rates via this NSED plumathon study. And so we looked at 40 different papers. NSED rates did vary between 70 and about 16,000 gallons per acre per year, with a median of around 1,000 gallons per acre a year. It was measured at all the sites in the literature. There were no differences apparent among the fuel types. And again, we found that if you apply any of those 4 commonly applied methods, you should get your true answer within about a factor of 3 to 5. And so thinking about the benefits to the Department of Defense, NSED, it is a measurable process. It's now been documented at numerous sites around the country and the world, and it can serve as a viable passive remedy at low-risk sites. And so I think the NAPL 3 document from ITRC does a really good job of that. And there has been a recently published ASTM standard on NSED and measuring NSED processes that was published in December of 2022. Temperature-based methods can measure NSED underneath paved surfaces, and so this opens a whole nother area sites that we can investigate, and we can measure these NSD rates to support these passive remedies. And then finally, newer sensor equipment, it can measure environmental variables of interest in near real time. Again, data backup is a key consideration, but this allows us to collect data without constantly sending people out to the field. So there's some cost considerations there. There's also some sustainability and health and safety considerations, because you're not always sending people out to the field to collect sparse data. Instead, we can measure this at fairly high temporal resolution and in real near time. Acknowledgements. I want to thank our principal investigator, Dr. Tom McHugh, Skylar Robinson, Poonam Kulkarni, Chuck Newell at GSI, Colorado State University, Kwan Karimi Askarani, who is now with us at GSI, and Dr. Tom Sale really were instrumental in a lot of the algorithms that we did and support. Travis Lewis with Navy NAFAC, and David Gent with U.S. Army Corps of Engineers were very helpful with site selection and other processes. Justin Meredith with the Tennessee DEC has been really helpful from a regulatory perspective. And also just want to make a huge shout out to all of our base contacts, Troy Johnson, Paige Walton at the Tuella facility, Samantha Malinky-Gertz at the Minnesota facility. Particularly when you consider their first demonstration project was that we were supposed to be in the field the last week of March 2020. That did not go according to plan. And they were both really instrumental in eventually getting us base access when it was safe to do so, and making sure that we could get this project rolling in a safe manner. And so they helped throughout the duration of the project, and it really couldn't have been possible without them. For additional information, please visit our ESTCP website. Again, hopefully that final report will be up here shortly. We're also finalizing a user's guide that will be available there for more information as well. And with that, I'm happy to take any questions.
Thank you so much, Nat. We've received a bunch of questions. The first one is from the U.S. Navy. Are temperatures at the water surface or VADO zone the primary regions where NSDD would be measurable, or would it also be measurable throughout the water column?
So most of the temperature difference is actually going to be in the unsaturated zone above the water table. And so when we conceptually think about an NAPL, we think about it as floating on top. And so you do see some temperature in the water, and we will certainly measure that gradient as it moves downwards. But the most of the peak in temperature is actually going to be in the unsaturated zone above the water table. And we've measured that in shallow water tables, 10 feet below ground surface. We've measured it in deeper water tables. I think the deepest we've done it is around 50 feet below ground surface, but we do see that measurable temperature difference based on the biological activity, and we can measure that gradient.
Thank you. And a follow-on questions from Subsurface Insight. How long are the temperature probes at your 2 demonstration sites?
I assume by how long it means how deep. And so I believe at the first site we installed them, the deepest was about 25 feet. And so they were installed about every foot for the first, say, I think 18 feet. I'd have to look at the actual diagrams, and then about 2-foot spacing once we got into groundwater. At the Minnesota site, it was a little bit shallower. 16 to 20 feet was as deep as we went there before we hit bedrock in the water table. And then I should have mentioned the demonstration period for the temperature monitoring was about 2 years at the Utah site and about 1.5 years at the Minnesota site.
Thank you. A really good question here from the U.S. Navy. Have you found regulators to be generally receptive to NSDD approaches? Yeah, and it's so, in our experience, it's been a mixed bag. Part of that depends on where you are. I think at the low risk sites, particularly where you've done some active remediation and it's just not doing much anymore, and your NAPL transmissivity is very low, there has been some receptivity to NSDD processes and monitoring NSDD akin to a monitored natural attenuation and groundwater type framework. And other jurisdictions, there's been less interest. I think over the last 3 or 4 years, we've really seen more and more of these guidance documents coming out. And so, we're really working on educating our regulators, helping them understand the processes and answering them questions. That's something that's an ongoing process.
It does depend jurisdictional too, if you have a requirement that you have to remove all NAPL in a well that's greater than say 0.01 feet, they're less receptive to an NSCD process if that's just their requirement than other facilities or other states where that may not be a requirement. But it is an ongoing process for sure.
Thank you so much, Nat. A question from EPA. Does NSVD occur if the LNAPL is confined?
That's a good question. We have seen some NSCD processes even in a confined scenario, and generally it's going to have some biodegradation, and then those gases will work their way up to the ground surface, and so where you'll still get a methane oxidation front even in some of those scenarios.
Great, thank you. This is a question from Scott Contracting. Would Ardina weather monitoring systems or similar systems work for capturing the data needed for the program described?
They should, and so it wasn't an Arduino that was used as the data management. It was I think it was a particle board, but it was a similar type concept. And so there's definitely a lot of ongoing work in these IoT type sensors, both the sensors themselves as well as the data chips that are recording that data and processing it. Again, we think if you're going to take that approach, it's really important not just to rely on any data connectivity that those platforms may provide, but also make sure that you're locally capturing all of that data in the event of data connectivity issues.
Great, thank you so much. Some more general questions. Can you speak to the cost considerations for implementing or employing the temperature-based method?
Sure, that's a great question. So, for the data monitoring and analysis, it's about on the order of $10,000 to $15,000 per year to get the data, to process it, to make sense of it all. And then the other costs are going to be the install. And so I think right now, just buying the hardware and the sensors at one monitoring point is roughly around $10,000 to $11,000. We've seen quite a bit of inflation over the last year or two in those systems, just like we've seen in the general public. And then if you can install them in existing monitoring wells, that approach has worked. But if you want to install them in a dedicated borehole, then you would have drilling and IDW considerations on top of that as well.
Great, thank you, Ness. You mentioned that your final report will be posted in a few weeks to your project webpage. Does this report have general information about NSVD, or can you please mention any other available resources or guidelines on NSVD or thermal NSVD?
Sure. Our final report has a brief overview of NSVD processes, but it's really focused on the specific data analyses at our 2 demonstration sites and the multi-site study. We are working on a user's guide that is more general, and that will speak to how to determine whether you should measure NSVD, and if so, which of the measurement methods may be particularly applicable at your site. And so that may be a very useful document as well. Appendix B to the 2018 ITRC LNAPL 3 document has a really good overview of each of these methods and how they're employed. And definitely check out the new ASTM standard that was published back in December. It walks through all sorts of considerations for the technology selection and walks through in a bit more detail each of the key techniques. There are some other guidance documents out there. I know API has a publication from 2017 on NSVD. CRC Care out of Australia has a good guidance document. Claire out of the UK also has a good guidance document as well. So there's 4 or 5 good resources. Those are all mentioned in our final report, but definitely some good avenues to learn more about the temperature-based method, but also all the other methods as well.
Great. Can you speak really broadly on how one can determine if and which NSVD method is appropriate at any given site?
Sure, and this is one of the issues that we're trying to tackle head on in that user's guide. And so, we think if you've got a really low risk site and you know that you don't have much recoverable LNAPL, I would point to literature values. Everywhere we've measured NSED, we know that it's occurring, and that may be sufficient to support using NSED. If you've got a site, it's relatively low risk, it's well characterized, you've got a regulatory environment that's very conducive to NSED, then maybe taking 2 to 4 sort of short-term snapshot measurements, say with the carbon traps or the DCC systems. If you have existing soil vapor monitoring probes, then you could use those using either the quantitative gradient method or even just qualitatively, as we talked about here. You can also use temperature measurements in a snapshot mode, particularly in monitoring wells. And then if you have either a more complex site or there's more regulatory or community interest and there's more of a need for longer term measurements, that's where we think that the temperature-based methods in particular are uniquely suited. And so some of it's going to depend really on the regulatory support as well as just the overall risk to human health and the environment from that particular LNAPL release.
Great, thank you so much, Ness. We have a few more questions that have come in to the first team. So while we're waiting for more questions for you, I'm going to pull Bo, Mark, and Mike back into the discussion. And we'll start with a question for Mark. Can you tell us if the modeling is applicable to NSZD of LNAPL, specifically the model that you guys are describing? Would it be applicable to next work? Bo or Mark?
Well, yeah, if Mark's not there, I can certainly answer that. Yes, absolutely. So it would be on the groundwater side. So if you had a floating NAPL, then you would get a dissolution rate on the underside into the groundwater. So that's where we have a mass transfer coefficient. And we've actually been pursuing this area and then also looking at what would happen if you increase the degradation rates and how that increased reaction would increase the enhancement. I mean, this is a good example of how sorry, I'm going to take 1 second and say, the purpose of our project was to show that this simpler approach could provide modeling that's of these complex processes that was equivalent to numerical models. The beta version models are simple versions, but we just wanted to show that you could keep incorporating all of these complexities like the fractured bedrock and things into the same framework. But we're not providing it all these complexities in the model, but natural source zone depletion, absolutely.
Great, thank you. One more question for you, Bo, and then we have a question that came in for Ness. What are the primary limitations for your model, and in which situations is it not applicable?
Well, again, as I said in the talk, that it's, the NAPL is residual. So that, so we're not looking at moving NAPL or trying to pump a NAPL out. And then like with the demo site, changing, we're trying to predict out, a couple of centuries what site conditions are going to be like. It doesn't look at changes like what if the water table now drops 100 feet. So things like that. And then, I mean, those are the main things. You can handle all these complexities. It's just not in the beta version. Like I said, even a DNAPL and a clay seam, or in the beta versions don't handle a mixture of soluble compounds at this point. Although we demoed a site with that and demoed experiments. But the limitations are really on the beta version, but we've successfully demonstrated the methodology. You can get it to a system of first order equations and solve it.
Great.
Without
Thank
resorting
you so
to
much.
the numerical models.
Thank you. And one last question for Ness before we wrap up. Are there any opportunities to combine the monitoring of an SED with any active treatment technologies monitoring program?
Yeah, absolutely. That's a great question. I think there's two components to that. Anytime you're enhancing that biodegradation, that'll increase the heat signal. I remember one of the early applications we were looking at the temperature data, and there was a pretty good 2 to 3 degrees Celsius increase above background, and then all of a sudden it jumped up to 8 degrees Celsius. We were all scratching our heads, and we reached back out to the site managers, and unbeknownst to us, there was an SVE system, and so they were pumping all of that oxygen down into the subsurface, and that was enhancing all of that biological activity. And so we were seeing a much bigger heat signal because of that. And so if you're enhancing the biodegradation, you should get a higher heat signal, and so you should be able to measure that with the temperature-based methods. And so you'll be measuring a combination of sort of the natural processes as well as the enhanced processes. I think the other component to that is, because it's a bacterial process, anything you can do to enhance the conditions of those bacteria will also enhance overall biodegradation. And so if you can do low-level heating of the subsurface, or we've had sites where they put surface covers on, like a ginormous tarp, or some sort of plastic sheeting to increase the subsurface temperature. And in those situations too, you've seen where you've increased that temperature, but you've also increased that biological activity and thus enhanced the natural rates that are taking place.
Great, thank you, Nat, and thank you to all of our 4 speakers today. We're going to go ahead and wrap up, but before we do that, I'd like to remind you that these webinars happen every 2 weeks. And our next webinar is on Thursday, February 9, on DoD-funded research to solve issues with gas turbine engine ingestion of dirt particles that can erode compressor airfoils and significantly impact engine performance on military aircraft. This webinar will feature 2 speakers, Mr. Greg Kroschenstein from the National Center for Manufacturing Sciences, and Mr. Marcio Duffels from NDS Coating. Please visit the StartUP and ESTCP webinar webpage to register for this and other webinars through the end of the year. I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your participation.